Perfect. So today we have Justine Kaidi tell us about exceptional moduli spaces for exceptional n equals to 3 theories. Take it away.
Okay, so thanks so much for having me. It's a pleasure. So today I will be talking about this work that was done in progress with my fantastic collaborators, Mario Martone and Gabby Zafrir. Gabby's actually in the audience. So the broad topic of the talk is going to be n equals 3 theories. And I think that basically anybody who gives a talk on 4D n equals 3 theories is legally obligated to start with the following sentence, which is that it was long believed that there were no purely 4D n equals 3 theories. And the reason for this belief was simple. If you just look at the list of free CPT invariant n equals 3 multiplets, it's the same as n equals 4 multiplets. So in other words, there's only vector multiplets and the content of the multiplets is the exact same. So if you try and write down a Lagrangian with these ingredients, then you're automatically going to have n equals 4. That's actually a little bit too quick because just because the multiplets are n equals 4 doesn't mean that all the interactions you write down will be n equals 4. But a little more hard work can show that indeed this is the case. And so any Lagrangian n equals 3 theories are also automatically n equals 4. But this doesn't rule out purely n equals 3 theories, which are non-Lagrangian or strongly coupled. I suspect that this was known or realized a long time ago, but the first place that I've seen it actually written down is in this paper by Aharoni and Evtechiev. So actually shortly after this paper appeared, so this paper simply pointed out that pure n equals 3 theories, which are strongly coupled, could exist. They didn't actually give any concrete examples. And, but shortly after this paper, some concrete examples were discovered. This is due to Garciá-Extebarria and Regalado. And the way that these were constructed was via so-called S-folds in type 2b. So I'll give a brief review of S-folding at some point in this talk. But suffice it to say that these authors were able to give a construction for purely n equals 3 theories. And after this work, there was a flurry of work on the topic. And so, for example, these authors soon after gave a follow-up work where they constructed more n equals 3 theories in M theory. And there were other works as well. Sorry, was there a question? No. Okay, good. So though there has been a lot of follow-up, I think that it is fair to say that the full space of n equals 3 theories remains largely unexplored. And one thing that I'm going to try and do today is to give you some picture for how one could go ahead and classify n equals 3 theories. Okay, and well, actually what I'll really do for you is just review a classification that already existed and then actually show you how to construct some of the theories in that list. Okay, so in trying to classify n equals 3 theories, it's useful to first try to classify their moduli spaces. Now, it's generally assumed that the moduli space takes the form of an orbifold. So locally, you have flat space C3R. R is called the rank of the theory. But globally, you have a modding out by some finite group gamma. Okay. And this gamma can't be anything. It has to satisfy some conditions. In particular, subject to some assumptions that I'll say in a moment, it has to be a so-called crystallographic complex reflection group, or CCRG for short. So we're going to unpack what exactly a crystallographic complex reflection group is, so don't be too worried. But let me just tell you briefly why it has to be this thing. So this crystallographic condition means that this finite group is a subgroup. Well, let me say it this way. This finite group leaves invariant some lattice in C3R. Okay? And this is interpreted as the electromagnetic charge lattice space. So this crystallographic condition is the condition that the monodromies on the moduli space are just valued in the Montan and Olive duality group of any generic point on the moduli space. We'll see more detail in a second. Okay, and what about this complex reflection condition? which again, I'll explain more later. But roughly speaking, this complex reflection group condition comes from the fact that I'm assuming the space takes the form of an orbifold. And I'm also making one more technical assumption, which is that the coordinate ring is freely generated. So if I assume orbifold and freely generated coordinate ring, then there's an old theorem in math due to Chevali and Shepard and Todd, which says that gamma has to be complex reflection. Okay, so this is some math condition. Now, one of the assumptions that went into this freely generated assumption here, is something that one could debate. Okay, for example, n equals 2 theories, it's not always the case that you have a freely generated coordinate. And in the n equals 3 case, there's actually seemingly a counterexample by these authors here. So I think it's still sort of up in the air whether this is actually for sure a counterexample or not. But suffice it to say that it has actually been conjectured that n equals 3 superconformal field theories are in one-to-one correspondence with CCRGs, okay, which would mean that this assumption is true. Okay, so I'm going to take this conjecture just as our starting point for this talk. So you might have some reservations about this that we can discuss later. But for today's talk, I'm going to assume that indeed n equals 3 SCFTs are in one-to-one correspondence with these crystallographic complex reflections. So then if I tell you what the classification of crystallographic complex reflection groups is, that will be equivalent to giving you the classification of n equals 3 superconformal field theories.
Could I make a comment?
Yes, please.
Which is that the assumption that the coordinate ring is freely generated is almost certainly not, is just a restrictive technical assumption. There are certainly physical theories without freely generated coordinate rings on the Coulomb branch.
I think the statement for n equals 3 is that that's not the case, at least up to discrete gaugings.
Yeah, well, what I'm talking about are discrete gaugings.
Ah, right. So then, yes, I agree. But I guess there's two comments I can make there. Of course, I won't in general be able to rule out having discrete gaugings, but yeah, one thing that I'll say is that if you do have a theory which is a discrete gauging of some other theory, there's always a discrete gauging you can do to go back. In this case, if you have a theory which is a discrete gauging of some zero form symmetry, you can always discretely gauge some two form symmetry to go back. So in some sense, I could still say that this classification would hold up to discrete gaugings of some higher form symmetries.
So that's a conjecture, and it may be true, but yeah,
that's true. Yes, yes. So
what's the big deal? Freely generated or not? We deal with so many moduli spaces. The generic thing is that the moduli space is not freely generated. Sometimes it's a complete intersection, but what's the big deal? Why are you making a point about this? What's the physics behind it?
Well, no, it's not so much a physics point as it is a classification point. So if I assume freely generated, then I can also assume that it's a complex reflection group by this Chevali-Shepard-Todd theorem. And those have been classified. So then I can just use the classification results there. So for now, you can just think of it as input into a classification problem and then try and restrict it later.
But because you're in n equals to 3, that you're trying to use this. I mean, moduli spaces appear all over the place, and it's a computation of the ring structure that tells you whether it's a complete intersection or not. You just compute the space of invariant functions.
I don't think that, I don't think that it's an issue about this. Is he's making a conjecture that up to this discrete gauging, that Coulomb branches, at least of n equals 3 theories, all have this special property that they have freely generated coordinate rings.
Yes. Well,
I personally think this is a very, or somebody's making this conjecture.
This is a result of a computation.
Yeah.
I'm quoting. Sorry?
Sorry, I was just saying I'm not making the conjecture, I'm quoting conjecture.
I see. Well, but this is a result of a computation, right? If you want to compute the space of invariants of a theory, you just compute the space of invariants, and then the result is either really generated or not.
Sure. I mean, I think the difficulty here is that we just don't, know anything about these n=3 theories. We're just we're trying to start from the bottom up. We're trying to start from the moduli space and construct the theory. We don't have a theory and then we can, construct its moduli space.
So you say you don't have a Lagrangian, that poses some difficulties.
No, we don't have anything. We're just literally starting from moduli spaces, and we're going to try and construct some non-Lagrangian theories out of that have those moduli spaces.
Mm-hmm. Okay.
Okay, great. So, right, now I share the reservations here. So if you also have reservations about this, you can feel free to think of this as a classification of some n=3 theories. And that's completely fine too. So from that point of view, you can say that today I'm going to try and show you how for every, or at least most, crystallographic complex reflection groups, you can get n=3 theory. Okay, whether or not this is the full space, well, that sort of depends on this conjecture here. Okay, so great. So I'm going to tell you what crystallographic complex reflection groups are first, and then I'm going to tell you how to go from those to n=3 theories. All right, great. So what's a crystallographic complex reflection group? Well, first, let me start very basic. What's a reflection? So a reflection, we all know, is I take some coordinate x and I send it to -x. More generally, if I have a vector of coordinates, then I send x to mx, where m is some matrix which has a single -1 eigenvalue, and the other eigenvalues are all 1. Okay, so that's what I mean by a reflection. Now, what's a complex reflection? A complex reflection is very similar. I take a coordinate z, say, and I change it to e⁻² pi over kz. So I shift it by some kth root of unit. Now, more generally, if z is a vector, then I take z to mz, where m is a matrix which now has a single kth root of unity eigenvalue, and all the other eigenvalues are. Okay, so that's what a complex reflection is. And a complex reflection group is simply a group which is generated by complex reflections. Okay, easy. So that's what a complex reflection group is. Let me give you an example which will recur throughout this talk. So there's this group G4, which is defined as follows. I have generators S and T, such that S and T cube to 1, and I have this commutation relation. Okay, so I can take an explicit matrix representation of S and T satisfying this. So that's given here. You can check that indeed S cubes to 1, T cubes to 1, and this is satisfied. And if you look at what the eigenvalues of these matrices are, they're both 1 and e⁻² pi over 3. So in other words, they're both complex reflections. Okay, so G4 is a complex reflection. All right, let me give you more examples. So consider the transformations which act on a vector in Cn, okay, some n vector. And the group we're going to discuss is generated by the generators of the permutation group Sn, acting on this, as well as one extra matrix, which is this kth root of unity times the identity. So at this point, you should stop me and say, oh, but M is not a complex reflection, because it doesn't just have one kth root of unity eigenvalue. All of the eigenvalues are kth roots of unity. But it turns out that by combining some of these generators with this guy, by dressing it properly, you can make it a complex reflection. So anyways, this group can be generated by complex reflections, even if I haven't given that representation. Now, okay, so anyways, the group that I get out of this is labeled by two numbers. It's labeled by n, okay, it's the rank, and it's labeled by the k, which labels this extra element m. Okay, so I'll get in this way an infinite family of complex reflection groups, which are denoted by G, K, 1, N. Okay, so this gives me an infinite family of complex reflection groups. And in fact, I can generalize this infinite family in a straightforward way by changing M slightly. And I change it in such a way that it depends on some extra number P. Okay, the details here are really not important, but you can see that it's fairly simple. And this generalization gives another infinite family called GKPN. So this infinite family is just a special case of this one. Okay, so these are just some examples of complex reflection groups. Now let me tell you the full classification. So the full classification was achieved by Shepard and Todd in the 50s. And it turns out that the full set of complex reflection groups is this infinite family, GKPN, that we just introduced, together with 34 exceptional cases, which are usually denoted GN, where N runs from 4 to 37. Okay, so for example, our friend G4 here is the simplest exceptional complex reflection. Okay, so that's what a complex reflection group is. Now I told you that for 4D n equals 3 theories, what's relevant is really the crystallographic complex reflection groups. So which of these groups here are crystallographic? Okay, for the infinite series, GKPN, it turns out that these are crystallographic if and only if K is 1, 2, 3, 4, or 6. Okay. And what about the exceptionals? Well, of the 34 exceptional complex reflection groups, 16 of them are crystallographic. Okay, and I've written those 16 down here. So for example, G4 that we met before is crystallographic, and so on and so forth. Okay. Now, you can see that there are some colors in this table. So let me say something about the colors. So the red color here represents cases which are actually Weyl groups. Okay, so this group here is actually the same as the Weyl group of E6. This is the one for the Weyl group of E7, E8. This one is a Weyl group for F4. Okay. So for our purposes today, these cases in red are actually not super interesting. So why? It's because the theories, if I have a theory whose moduli space is labeled by one of these Weyl groups, I already know an n equals 3 theory which has this property, which is, in other words, n equals 4 super Yang mills of type G. Okay, so it's not a pure n equals 3 theory, but it is n equals 3. And so actually, assuming that this map between crystallographic complex reflection and n equals 3 theories is 1-to-1, which you might debate, but that's the conjecture. So then we already know the n equals 3 theories corresponding to these cases, so I don't need to discuss it anymore. And so for today, I'm going to basically ignore the cases in red. Okay. Instead, what's more interesting is to focus on these other 12 cases. And in particular, the ones in green are the ones which I'm going to be really giving you explicit n equals 3 theories for. Okay, so the ones in green will be our targets. But anyways, this conjecture, again, is that for every one of the crystallographic complex reflection groups, which are just all on this slide here, so for every group on this slide, there should be an n equals 3 theory. Okay, so that's the idea. But actually, for the majority of these cases, the corresponding n equals 3 theories are not known. Okay. In particular, there is or was no theory known with a moduli space labeled by an exceptional crystallographic complex reflection. Okay, so one of the ones in here. There's no known theory. So today, in this talk, I'm going to have two goals. The first goal is going to be the following. Just assume the existence of n equals 3 theories with moduli space labeled by an exceptional CCRG. Okay, just assume they exist. Then on the basis of group theory alone, we'll be able to derive many of the properties of the corresponding n equals 3 theories. We'll be able to figure out their central charges, their spectrum of operator dimensions for the operators parameterizing the moduli space. We'll be able to get the stratification of their moduli spaces, and we'll be able to guess potential constructions for these things in, say, string theory. And then the second goal of the talk will be to show that, so after we guess some M theory realization, we'll argue that these theories are actually the exact same as theories that were already found by Garciá-Extebarria and Regalado for the most part. So in this paper, they just sort of gave some abstract M theory construction without discussing moduli spaces or central charges or anything. But we'll make contact with their work, and we'll give M theory realizations for 8 of the 12 theories. So in particular, these 8 cases that were in green. Okay, so that's the goal. Are there any questions about the goal before I get to part 1? Okay, so now I'm going to tell you how, just based on group theory alone, we can learn a lot about these tentative n equals 3 theories. So I want to begin with an extremely trivial warm-up, just because I think it's going to be very helpful to understand what's going to happen today. So the warm-up is the following. We're going to just begin with some stack of n D3 branes. Okay, what can be easier? So here's my stack of branes. Okay, there's n of them. And so what's the moduli space of the theory that lives on this stack? Well, geometrically, I have n branes, and each brane, so I'm in type 2b, there's 10 dimensions. And so there's 6 transverse directions. So for each brane, there's a C3 of sort of transverse motions. And so since there's n branes, then I would guess that the moduli space is C3n. Okay, locally, this is correct, but we all know that branes are indistinguishable. So I really have to quotient this by the permutation group on the branes, so Sn. And so the moduli space in this case is really C3 mod Sn, C3n mod Sn. Okay, so there's another way to get this result. Okay, this was sort of the brane picture. There's obviously a field theory picture. So I can note that Sn is the same as the Weyl group of An minus 1. And so I can write the moduli space as this. And then the way I can think about it is sort of as follows. So the theory that lives on the moduli space, that lives on the D3 branes is n equals 4 An minus 1 super n minus. And then I can just use the fact that G type n equals 4 super granules has moduli space C mod the Weyl group of G. So in this case, it's the Weyl group of A. Okay, so that's another way to say it. So a generic point on this moduli space here is given by some diagonal matrix with the entries being phi1, phi2, ... to phi n, where each of these phi's you can think of as parameterizing the transverse directions of one of the branes. Okay, so each phi I is in C. Okay, so that's the easiest case. It's just a stack of D3s. Now let's go to something else which is familiar, but slightly more complicated, which is an orientifold. So the starting point for an orientifold is we'll take 2n D3 branes. And so by the statements I just made, clearly the moduli space is C6n mod Weyl group of A 2n. So I just put 2n instead of n. Now I do the orientifold. So let me draw it again. So here's my stack. Here's one stack of n branes. Here's another stack of n branes. And when I do the orientifold, I require that each brane on the top stack has a mirror pair, a mirror partner on the bottom stack. So what that means is that before I had C6n locally, and after I'll have C3n. Okay, I've cut out half of the moduli because when I move this guy, one of the guys down here is constrained to move with it. Okay, so locally the moduli space is C3n, But globally, I have to do a quotient. And what am I supposed to quotient by? Well, each brane in this stack is indistinguishable. So I have to quotient by Sn, or in other words, the Weyl group of A minus 1. But now there's an additional thing I have to quotient by, which is the fact that, so for each brane here, I can either move it up or down. But actually the motions down can just be thought of as motions sort of up of the mirror brane. So in other words, I have to identify phi I with minus phi I. Okay, so I have to quotient by an extra n copies of Z2 for each of these sort of phi goes to minus phi. Okay, so the actual moduli space in this case is C3n mod the Weyl group of an minus 1 times Z2 to the n. Okay, and actually this Sn, this permutation part, permutes the n copies of Z2, so it's a semi-direct product. Okay, so I just gave you the brane picture for the moduli space here. There's again another way to interpret the moduli space, which is that I note that this Weyl group of an minus 1 times Z2 to the n is actually the same as the Weyl group of Cn. And then I can remember that the world volume theory of d-branes probing an orientifold is going to be, well, it depends on which type of orientifold, but basically it's going to be Cn or say Bn super Yang mills. Okay, and so the Weyl groups of Cn and Bn are the same, so either way I get this. There's also technically a Dn case, which is slightly more subtle, but it's not going to be important, so I'm not going to say anything. Okay, so we saw how to get the moduli space again for an orientifold. So we're going to go to S folds in more complicated cases now. So before doing complicated stuff, I just want to really take the salient features of what we did here. Okay, so what was the two-step procedure that we used to get the moduli space? And the two-step procedure was the following. We began by taking our vector in the enlarged moduli space, C6n, or C6n with some quotient. And then we restricted to a slice. Okay, we restricted to the slice where we have mirror pairs. Okay, and that restriction to that slice can be rewritten as this equation. Minus phi is equal to phi up to an element of the Weyl group of A2n minus 1. Okay, just to really drive the point home, if phi looked like phi 1, phi 2, ... then either I could have phi 1 is equal to 0, which means the brane is on the orientifold, and then clearly minus this is equal to itself. Or I could have phi 1 non-zero, in which case there needs to be a mirror pair, and then minus phi acts as a permutation on these two. Okay, so it's an element of this. Okay, so the first step was to work in the enlarged moduli space, take a slice, which has the correct mirror pairs. And then the second step is that I then quotient the resulting moduli space, which it would be C3n. I quotient this result by the subgroup of A2n minus 1, which leaves this slice invariant. Or I should say, sorry, it maps the slice to itself. So it leaves the slice fixed. Okay, that was the two steps. Restrict to a slice, mod out by the subgroup of the enlarged Weyl group, which leaves the slice fixed. So
I'm waiting to hear about statistics and symmetric products. I haven't heard anything about that.
Sorry, symmetric products?
This problem is completely trivial. All of the steps that you described now are completely trivial.
Yeah, so I'm just going to apply them to non-trivial cases. I mean, I'm trying to motivate it.
You don't see that there are symmetric products over here?
Symmetric products of what, sorry?
Of whatever space that a single brane sees. So if it is without an orientifold, you have a symmetric product of C3. If it is with an orientifold, you see it's always a symmetric product of the space that a single brain sees.
He did say this. He showed us
Yeah.
to the 3n, where n is a number of brains, and then it's modded by the Weyl group. So that is a symmetric product.
Yeah, it's not using this language. But okay.
No, I said that, but that's not. It's not going to generalize. I'm going to show you how to now get complex reflection groups here instead of symmetric.
Mm-hmm.
I'm just trying to convince you that, so I'm just trying to remind you that there's these two steps, which are trivial, as you said, and now I'm going to apply them to non-trivial cases. And I'm going to get complex reflection groups out.
By applying the group action on the coordinates, I don't see where is the non-trivial step.
Okay, well, so I'm just going to tell you how to get complex reflection groups here.
Could it be because you're going to use the intrinsic gauge group as opposed to the orbifold of the transfer space? You're going to think of it in terms of Weyl groups as a gauge group, and then that's why you'll be able to extend it to exceptional cases, right? I mean, that's
exactly.
That's how you're shifting the paradigm. I mean, I think. Right?
Yeah, I'm trying to motivate it in terms of these cases with brains that we know, but then I'm going to go away from the brains to the exceptional case.
Yeah.
Well, just remember the group you're talking to. Yeah. You know, this is what we do for living. This thing. So it's all up to now was really trivial.
Yeah, but you don't do it.
I know, but I'm just trying to give you the background. So okay, maybe okay. So I mean, do you know how to already get the complex reflection groups out?
If you just give the action on the coordinate ring, the computation of the modular space becomes trivial. It's a simple computation.
Okay.
If you are doing it in a different, let's hear.
Okay. Maybe we can move forward and we'll see what happens.
Okay.
I might not tell you anything new that you don't know that.
I mean, if you have brains with exceptional gauge groups, like from F theory, right? Then you probably don't know how to do it with your technology, and Justin probably does, right? That's what
I'm not trying to.
You have a continuous action, you have a discrete action, you know how to apply this, and you just compute. It's straightforward.
The issue isn't the construction of the orbifold. That is straightforward. It's given by the complex reflection group action.
Yes.
The question is, what's the string construction of the corresponding thing? And that's something less trivial that he's going to tell us.
I'll be open to. Okay, let's see.
Okay. Okay. Well, okay. So I'm trying to build up to the string construction. So I'm trying to make sure that we're on the same page. So I'm going to do the same two-step procedure for the S-fold and see how we get the complex reflection groups of standard type, and then I'll show you how to get the exceptional ones. And then we'll guess the string theory construction from that. Okay. So I'm going to do the same thing I did for the orientifold, for the S-fold. So an S-fold, a ZK S-fold for K 2, 3, 4, and 6 is obtained as follows. I start with Kn D3 brains, and then I do a ZK quotient. Okay. And so then I have the same exact two-step procedure as before. Okay, so I start in large moduli space C3Kn, and then I restrict to the slice where I have the correct mirror pairs. Okay, so for example, if I have a Z3 quotient, then I should have 3 mirror pairs. So restricting ourselves to this slice means that I impose this constraint on the fields in the enlarged space. Okay, so that will restrict me to a slice parameterized by C3n. Okay. And then once I have this slice, I then quotient by the subgroup of the larger Weyl group, which leaves this slice fixed. Okay, which again, it's just some group theory problem. You can do it on the computer, or you can just think about it, and you can figure out that the subgroup of this, which leaves this slice fixed, is Sn. It's the permutations. So write each brain here. So each thing here was a stack of n brains. So I have the permutations amongst those n brains. And then I have n copies of zk, okay, which basically tell me that I can switch the brain with its mirror pairs. And so I have to quotient by this here. And this gives me, this is one way to get the result. And the other way is to note that this thing here is equivalent to the complex reflection group GK1N. So we conclude that the theory living on these moduli spaces, on these brains, that is to say, the ZK S-fold theories of rank n have moduli space labeled by this set of complex reflection groups, GK1N. Okay, this is again, it's known. I'm just rederiving it for you because we're going to extend it. Right? But we can see that using this two-step process, it's now straightforward to get the moduli space, okay? If we have a brain construction. All right, and the key point here is that when we do this two-step process, what we can recover are theories where the complex reflection group is a subgroup of a Weyl group, right? So in all of the cases I just discussed, the complex reflection group was a subgroup of the Weyl groups of A-type Lie algebras, AKN-1. Okay, so now we can ask the following question. Let's say that I want to go beyond A-type Lie algebras. So more generally, say that I started with a theory with a moduli space C mod the Weyl group of some G. So for example, n equals 4G, super Yang Mills, where G is exceptional. So now I don't have a picture in terms of brains. I might hope to find an appropriate quotient sort of in quotes, but I mean something like the orientifold or S-fold, such that I can get an n equals 3 theory labeled by crystallographic complex reflection groups gamma for any gamma which is a subgroup of the Weyl group. Okay, so I might hope to do that. And indeed, we're going to see exactly how to do it. So we're going to see how to construct n equals 3 theories labeled by any CCRG, which is a subgroup of a Weyl group. Okay, and so first, let me just remind you which exceptional CCRGs are subgroups of Weyl groups.
When you say construct, what is the meaning of construction?
Okay, so eventually I'm going to give you the string or M theory construction. So I think that's what we usually mean by construct. For the first part of the talk, I just wanted to assume that they exist and then derive properties. But in the second part of the talk, if I get there, I'm going to tell you how to actually construct them in M theory by taking a 62,0 theory of type G and doing some appropriate quotient.
Okay, thank you.
Yeah, but that's the second part of the talk. The first part of the talk, I want to assume they exist and then derive properties just from group theory. It's literally just group theory, as you're saying. Just nobody did it. So I'm telling you that we did it and how we did it. Okay. Okay, so what's the list of exceptional CCRGs that are subgroups of Weyl groups? These are the guys that we're gonna see today. And so that's given in this table here. So for example, G4, our old friend, is a subgroup of the Weyl group of D4, and so on and so forth. Okay, there's some repeats here, but there's 8 in total. Okay, good. So, based on the way that G4 embeds in the Weyl group of D4, for example, we can already guess what its string construction should look like. Okay, so how can we guess? Well, the idea is as follows. Again, this is why I really wanted to drive home this trivial two-step procedure. So consider G4, which is a subgroup of the Weyl group of D4. Now we note, just as a group theory fact, that it can be obtained in the following way. It can be obtained by considering some vector phi in C12, and then restricting to a slice in C12, such that phi satisfies this relation, okay? So basically, some operator O, it's some matrix O on phi, gives you phi up to elements of the Weyl group of D4. Okay, so that's the first step. You restrict to some slice, and then you ask for the subgroup of the Weyl group of D4 which leaves this slice fixed. And so you can just compute this using gap or something. And you'll figure out that that subgroup is G4. So this is just one math way to get G4. I haven't told you the physics yet. But because I said it in this two-step way, it should seem very reminiscent of the, orientifolding and S-folding. And it should hint to us that a theory with moduli space labeled by G4 should be obtainable by doing some operation, which is captured by O, okay, on a theory with moduli space C12 mod the Weyl group of D4. For example, SO8 n equals 4. So what is this operation O? Well, remember, for the orientifold, O was -1. For the S-fold, it was 2 pi I over K. So in the current case, O looks like a Z3 S-fold, but then there's this extra matrix piece. Okay? And it turns out that this matrix piece implements the outer automorphism operation, or the triality of D4. Okay? So what this suggests, again, just from group theory, I haven't done any physics really, but what it suggests is that an n equals 3 theory labeled by G4 can be obtained from n equals 4 SO8 by doing some operation, which is like a Z3 S-fold plus some outer automorphism quotient. Okay, so this is, again, just group theory. Okay, and I can do the same sort of analysis for all of the cases to guess how I would construct them. Okay, so I just said G4. I can get it from starting with D4 and then doing a Z3 S-fold. The tilde here means that there's some outer automorphism quotient. Okay, and likewise, G5 can be obtained from E6 by doing a Z6 quotient, et cetera, et cetera. Okay.
Why are there only 8 entries in this table when there were like 11 exceptional Gs in the previous table?
Well, so that's just because this table.
Yeah.
This table has a double or like overlap. So
I see. Yeah.
G8 can be obtained from F4, E6, and E7. Mm-hmm. So yeah, and then you can also see that reflected in this table. So G8 could be obtained in 3 ways. Yeah, good question. Okay, so yeah, so this is how this is how you can guess the construction just from group theory, and you can actually do more just from trivial, group theory. So you can figure out what the spectrum of operator dimensions for the moduli space is. This is trivial. It's just given by the degrees of the invariant polynomials of gamma. So you can just look this up in Wikipedia. And indeed, I got this from Wikipedia. So, so you can get these operator dimensions. And once you have those, you can also compute the central charge. Okay. So there's this formula by Shapir and Tachikawa. There's some caveats if there's discrete gaugings, but I can discuss those later. But under normal circumstances, there's this formula due to Shapir and Tachikawa, which relates A and C central charges to the rank, which is just the number of invariant polynomials, and these deltas that I have listed here. And so using this formula, together with the fact that A is equal to C for n equals 3 theories, we're then able to also compute C for all of these theories. Okay? This is all just group theory. Okay, so we've managed, just by assuming the existence of such theories, to find potential constructions C and the spectrum of operator dimensions. And now we can do even more and figure out the stratification of the moduli space. Now, I was going to briefly, in 1 or 2 slides, introduce the notion of a Hasse diagram, but maybe people don't want me to review what a Hasse diagram is because everybody's an expert, and certainly more of an expert than me. So should I say what this is for people? Does anybody not know what a Hasse diagram is? Maybe I'll say it that way. Would anybody like a 1 or 2 slide review of it? If not, let me know. Okay, so everybody does know. Okay, good. So we all know what a Hasse diagram is. So I was going to give an example of a Hasse diagram, but I'm not. So let me just summarize what the example would have been, which is that I gave the example of G312. Oh, this is supposed to be G312. Reminded you what a Hasse diagram is. A Hasse diagram is just some, well, at first level, it's just some group theory thing you can do where you find the singular the stratification of the moduli space. Okay, good. So that's what the Hasse diagram is. And you can go ahead and you can compute the Hasse diagrams for each of these exceptional crystallographic complex reflection groups. There's no physics here again. There is physics afterwards, but at first sight, there's no physics. It's just a group theory thing. You just find the stratification of the moduli space. You look at the singular loci, etc. So for example, our friend G4 has a Hasse diagram that looks like this. There's one codimension one singular locus, and the theory, the rank one theory on that singular locus should have a moduli space, which is C mod C3 mod Z3. Okay. Now, once you have these Hasse diagrams, you can now do some non-trivial consistency checks on the proposed n=3 theories that would live at the origin. Okay, and in particular, those consistency checks are that you can use a very nice formula due to Mario Martone, which says that A and C of the rank 1 strata, so these strata which are first from the top, the A and C's of these guys are related to those of the theory at the origin. Okay. We already computed A and C for the theories at the origin, at least assuming they're not discrete gaugings. And now we can just search if there's any sort of rank 1 theory we can put on these strata such that we satisfy Mario's formula. Okay, this will give us a non-trivial consistency check. Okay, so in our context, what Mario's formula looks like is as shown here. Okay, so what it tells you is that 12C at the origin is equal to 3 times the rank in the current case. And then you have a sum here over the singular loci. So the rank 1, the codimension 1 loci. So this one here, or these two here, say. So you sum over that. And what's in the sum end? Well, there's one thing here, which is this delta I singular. This is just some group theory thing, but it's the degree of homogeneity of the polynomial specifying the singular locus. That's what this delta I is. Again, it's just a group theory thing. And finally, the last piece, the only piece of real physics in this formula is this BI. BI depends on what precise physical theory you put on the singular locus here. Okay. So it's something that you can look up or compute, but I won't tell you how to compute it right now. Okay, so anyways, let me now do an example to show how this all works out. So consider the G4 theory, whose Hasse diagram is shown here. We see that there has to be a rank 1 theory on the stratum, which has moduli spaces C3 mod Z3. So what theory am I going to put on this stratum? Well, there's two options. There's two obvious options for what I can put on this stratum. I can put the rank 1 Z3S fold, or I can say put a Z3 gauging of U1. Okay, I'll have to say some words about this discrete gauging in a second, but suffice it to say that I can go ahead and look at this B quantity, which is supposed to label these guys, and I find that B is equal to 4 for this guy, B is equal to 0 for this guy. And on the other hand, just from group theory, we had found already that 12C for G4 is 54. Okay, I didn't point it out, but it was in one of the previous tables. R is equal to 2, and delta singular is equal to 12. So now I can just plug those into this equation here with let's say B is equal to 4, and I see that it checks out. Okay, so that doesn't tell me that for sure the theory living here is a rank 1 Z3S fold. Okay, but it does say that a rank 1 Z3S fold would give a consistent configuration. So at least I can't rule this out. It could have been the case that my application of the Shapiro and Tachikawa formula was not justified. And so then I would have to go back and recompute the central charge, and then maybe I could get away with putting the Z3 U1 theory, Z3 gauge theory here. That's actually possible. So I can't, so all I'm saying at this level is that it is consistent with this being a non-trivial theory. Okay, so this, okay, so is everybody on the same page so far? So I've assumed the existence of these theories, used group theory to obtain central charges, operator dimensions, stratification of moduli spaces. And we also had guessed at some point their construction. And now I'm going to give you the string theory construction in remaining 5 to 10 minutes.
So for this moduli space,
yes.
I see that you're labeling nodes on the Hasse diagram with discrete groups.
Yes.
And what do you give meaning to the lines that connect each point?
So no, there's no, I mean, the only meaning is that, so this thing here is on a singular locus. So this thing here is on this, and this is on this.
And the dimension of the moduli space remains the same, right?
The dimension of the moduli space. No, so this is a, so this moduli space here is like C, in this case it's C6 mod G4, and here the moduli space is C3 mod Z3.
It's a Higgs mechanism, right? To go from the bottom to above.
Yes, exactly.
Yeah.
It's moving away from a generic, like from a less generic point to a more generic point as you go bottom to up.
And the top point is just the origin?
Okay, good. Well, so maybe I should have, yes. So no, the top point is not the origin. That
let me explain about Hasse diagrams is a generic term which denotes partial order. Now,
yeah, exactly. It's confusing. No, I agree.
Specify what meaning you give to points and what meaning.
Yeah, I completely agree. Sorry, I shouldn't have skipped this as much as I did. So yeah, let me give you my convention. My convention is that the point at the top represents the generic point on the moduli space. Then when I go down to the first level away from the top, I'm looking at codimension 1 singular loci. Now, the codimension 1 singular loci could, for example, intersect at a codimension 2 singular locus, and that would be represented by 2 lines going down to the same point. So this level here is the codimension 2 singular locus.
But with the description that you just gave, the red lines will have the meaning of some degeneration. It's a singularity by itself.
Yeah, I guess you could think of it like that. I just think of the lines as giving the actual partial ordering relation. So for example, so let's say I have this space here. So this is, you can think of as a picture of C6. And let's say I have 2 singular loci and they can intersect at a point.
Mm-hmm.
So the generic point on C6 is this point.
Yeah, so
then
the question is, how many moduli and what kind of singularity structure do you need to tune in order to move from the generic point to one of those green lines, right? So there's going to be a particular singular structure. And this is something that typically you could try to compute, right?
Yes, yeah,
conical singularity.
It's every nearest neighbor in the Hasse diagram is always tuning 3 moduli, 3 complex moduli in these theories.
Okay.
Yeah.
And it's of the form of C3 mod Z2 as we see here?
Yeah.
Or is it more complicated?
You're saying like the transverse slice looks like C3.
That's right. Yeah. So
exactly. Yes. This here is labeling the transverse slice. So it's telling me that the transverse slice is C3 mod.
So you have continuous sets of points, right? These typically are open sets. The transverse slice is a degeneration. Right? When you move from one set of points to another. If we deal with symplectic singularities, then we'll have leaves, but symplectic leaves. But we can call them leaves because those are open spaces. So the question is, what moduli do you need to tune from one open space to another?
But that's an additional question, right? I mean,
yes, right. If you don't,
it's just more things. Like maybe we can see what Justin wants to tell us, and can ask about transverse slices later.
Yes, I think that's fair. Yes.
Okay. Okay. Thank you. Are there any other questions on what I said so far?
I'm with you.
Okay. Thanks. Okay. So great. Then let me just quickly give you the string theory description. In fact, I can be brief here because, as I said, it's really a construction which is due to Garciá-Extebarria and Regalado, and I'm just going to basically show you that their construction can be used and maybe slightly generalized by outer automorphism twists to give us exactly what we want. And let me just remind you, because maybe so let me just remind you what we want, right? So what we basically wanted was we wanted to start a lot like the S-fold, where we had the stack of D3 branes and we do some quotient. We want to basically do that same thing, but we now can't, we want to start with the G type n equals 4 superunion mills. Okay, so we can't start with a stack of branes. But what we can do is, for example, start with the 2,0 theory and compactify to get n equals 4, and then do the quotient at the level of, so in that picture. Okay, so the first step that we're going to do is we're going to try to just take the usual S-fold and put it in M theory. Okay, because M theory, we can also nicely embed these exceptional n equals 4. Okay, so let's start with the usual S-fold, just stack of D3 branes with the Z-K quotient, and see how we do it in M theory. And then we're just going to generalize that to the exception. Okay, so so start with M theory on a 3 torus. Okay. M theory on TK has a U-duality group, which is some split form of EK. Okay, and let's just focus on the case we're interested in, which is where we have T3. And then so then M theory is going to have SL3Z times SL2Z symmetry. And let me point out, this SL3Z here is like geometric symmetries of the T3. And this SL2Z here is non-geometric. It's like the sort of T-duality piece. Okay. Okay, so now what I'm going to do is I'm going to insert an M5 brane into this setup. Okay, so I'm going to put an M5 brane on R13 times T2 in R17 times T3. And when I do so, I'm going to break the symmetry SO1, 7 times this thing I just told you, SL3Z times SL2Z. I'm going to break it down to SO13 times SO4, obviously. And then I'm going to break the SL3Z to SL2Z, okay, because I am focusing on a T2 and T3. That one's also obvious. And what's less obvious is that you'll also preserve this non-geometric SL2Z. Okay, I can give you the argument for why you'll preserve that later if you're interested, but for now, let's just say that you preserve it. And so this is the full set of symmetries that you have after inserting the M5 brane. Okay, now what we're going to do is we're going to consider 3 different ZK actions. One of them is a ZK rotation in the transverse space. There's a ZK quotient, a geometric quotient, a geometric Z3 that acts on the torus if I fix tau, the complex parameter of the torus, to specific values. And then there's a non-geometric ZK, which is a little harder to understand, but I can again explain it afterwards if you're interested. So there's 3 ZKs. And if I take the diagonal ZK, the diagonal of all of those, okay, I'll call that operation OK. Then I can quotient by OK. And this will give me the M theory version of a ZKS fold, it turns out. Okay, so this setup I just described is supposed to be exactly the same as the usual ZKS fold on a stack of D3 branes. Okay. And now we just want the exceptional version of this. Okay, and let me sketch for you the exceptional version of this construction. Okay, so it's going to be a multi-step procedure. We're going to try and go from this 2,0 theory to M theory, and then we'll do the same S fold as before. Okay, so the idea is as follows. I'm going to start with type 2B on C2 mod G, where G is a ADE finite subgroup of SU2. This will give me the 62,0 theory. Okay, and I'm gonna write the space-time in parentheses for each step. So at this step, the space-time is R15 times C2 mod G. Okay, now what I'm going to do is I'm going to compactify two of the directions of C2 mod G. Okay, compactifying two of the directions of C2 mod G will give me a T2 fibration over C, where the monodromy of the T2 around the origin is specified by this G. Okay, so what I'll get at this step is R15 times T2 fibered over C. You'll see why I'm doing this in a second. Now I'm going to compactify further on a second torus, and now the compactification happens in the R15 piece. Okay, so this will give me G n equals 4 super Yang mills on R13 times T2 fibered over C. And now I can T-dualize and lift to M theory. Okay, so I'll get like the M theory lift of this G n equals 4 super Yang mills. Okay, the space-time doesn't change compared to here, except that I now have the M theory circle. Okay, and now that I'm in M theory, I can finally do this S-fold that I wanted to do all along. The S-fold looks slightly different than it looked before. But it's basically the same. So I have one ZK, which is rotations in the transverse space. But now instead of the transverse space being C2, it's T2 times C. And then I can do some, quotient, some ZK that acts on the torus, T hat 2, and also some non-geometric quotient. And so suffice it to say, I can do this quotient, and that will be the desired S-fold. I might also have to do an outer automorphism twist, which I can explain later if you're interested. After I finish the talk. But okay, suffice it to say that this is how you can get the n equals 3 theories discussed in part 1. We give some more detail in the paper. Okay, so are there any questions before I start to summarize? I think I'm over time, sorry.
Yeah, don't worry about the time, you're good.
Okay.
So what you just outlined was Iñaki and Diego's exceptional S-fold construction?
Yes.
Is that right?
Yeah, the only thing that we've done in the paper is to just add epsilon to what they did, in the sense that we also show that you can do outer automorphism twists, which would effectively let you access the non-simply laced G n equals 4 super Yang mills theory, which they didn't have in the original construction. But yeah, it's just their construction really. And we've really just added epsilon to it.
Thanks.
Thank you. Okay, great. Any other questions? Okay, good, then let me summarize. So as I reviewed for you, n equals 3 theories are conjecturally in one-to-one correspondence with crystallographic complex reflection groups. These crystallographic complex reflection groups come in an infinite family and several exceptionals. And to date, nobody had ever showed that any n equals 3 theory had a moduli space labeled by an exceptional CCRG. So in today's talk, I gave it in 2 parts. So first of all, what I said was, assuming that theories labeled by exceptional CCRGs exist, then based on group theory alone, how far can we get? And I showed that you can derive operator dimensions, central charges, you can get the full stratification of the moduli spaces, and you can also guess some construction for them. Okay. And then after making that guess, we were able to show that this matches with the M theory construction of Garciá-Extebarria and Regalado, at least if I also include in the outer automorphism slight generalization. Okay, so one thing that I should say is that this construction, what I've told you, only let us access CCRGs, which are subgroups of Weyl groups. Okay, So that was, well, almost all of them. But there are still 4 remaining exceptional CCRGs, which are not subgroups of Weyl groups, which are these ones here, G24, G29, G33, and G34. And it would be very interesting to come up with some way to access these. Presumably can't be obtained by any sort of analogous operation to the one we used, because well, the starting point was some Weyl group. Okay, great. So that's it. Thanks very much.
All right, let's thank Justin. Questions?
I have a question, but maybe it's a little off
Sure.
In a different direction, which is that Corsi and Ciccati pointed out that that these CCRGs don't always admit principally polarized symplectic forms, Dirac pairings on their.
Yes.
And I was wondering if there's a relationship between these 4 exceptional guys that you can't construct this way, or if there's just there's no clear relationship between principal polarization and not.
Yeah, I think actually you can ask even amongst the ones which we have realized, which have principal polarization and which don't. And sorry, let me go back to the slide where I listed them, which was a while ago. Sorry. Okay, so we had this list. So actually, yeah, even in this list, so the ones that we realized are the ones in green, and not all of those have principal polarization. In fact, I would say that most of them don't have principal polarization. So this I think the G4 one, for example, if I recall correctly, doesn't even, but G12 does, and so on. So yeah, I could tell you exactly which of these do and don't later, but yeah, so even amongst the ones we have realized, they don't all have principal polarization. And I think maybe even most don't.
Interesting. Okay, thanks.
Yeah, thank you.
This G8 guy appeared in 3 different ways. Is this somehow a very special group?
You could say, I mean, it's special in the sense that it's a subgroup of 3 different Weyl groups, but
okay,
I'm not sure if it's much more than that.
Okay.
Yeah.
And can you show your Hasse diagram some more time?
Yes, sure. I actually didn't include all of the Hasse diagrams here. I didn't include all 8, but this is maybe 6 of them. Here you go. 5 of them, yeah.
Okay, yeah, I just want to, I don't have a specific question, I just wanted to see.
Okay, yeah, sure.
Okay. Do we have more questions for Justin? While we admire these diagrams? If not, maybe let's thank him again.
Okay, thank you.
So every line is 3 complex dimensional?
That's right, yes.
And the bottom is a point or more?
Sorry, could you ask one more time? I didn't hear.
The lower point is only a point, or it's more than just a point?
No. The top is the point, and the moduli space grows as you go down. So this one here would be 6. So
I see. I should go from up down.
Exactly. That's the that's the confusing convention that I was going to explain. Yeah. So you have to. This is a generic point on the moduli space, which is some trivial theory without any moduli space itself. So then this is the codimension 1 singular loci, which host rank 1 theories. So then this is C3. This is a codimension 2 locus, which hosts a rank 2 theory. So C6.
So I think if you to use the same language that Ami uses, the top point is actually the whole space. The next rank down are the codimension 1, which means really codimension 3, the closure of the codimension 3 loci, and the bottom is actually the closure of, say, the in the top view is the closure of the codimension 2 loci, which is indeed a single point. In other words, if you think of it in terms of of stratifications, you should think of the top point as the whole space.
Yes. But then the labeling is confused. Yeah, no, so I know 100% what you're talking about.
The labeling labels transverse slices, but yeah, you're right.
Yeah, no, yes, exactly. So you have to make a distinction between. Yes, you have to make the distinction of whether you're talking about the point in the moduli space or the transverse slice to that point. This is what I was trying to say. So this label labels the transverse slice. So if I have a point at the center, then this label tells me that the transverse slice looks like C6 mod G4. So it's a point in the moduli space. So you can think of it as that, or you can think of this as really the transverse slice. And that's what I don't know, in my mind, that's how I interpret this label.
Well, typically we associate the transverse slice to a line, not to a point.
Yeah, but here just think that from every point you draw the line all the way up, and then you just label the point with that instead of drawing the line. So it's just a different labeling, but it's the mathematics is the same in the physics.
So you want to denote the slice, which is the transition from the bottom to the top.
Yes. Yeah.
So basically on this you can trivially do this, because for every leaf there is a slice that goes to the top. So then just replace leaf with slice to the top, and that's the labeling here. This is just a choice of whatever you prefer, and there is a physical meaning because these are the things that you get from Higgsing. So these are the important slices, because you Higgs from, for example, on the right from the G25, you can Higgs to the G4 theory. I guess that's the idea, and then to the Z3 theory and so on.
But when you say Higgsing, you need to talk about the gauge group.
Well, I mean, a generalization of a Higgsing, then it's still a Higgs mechanism of some sort.
Higgsing just in the sense that you're turning on a VEV, even
you're
though
turning on a VEV and it breaks some.
In which to
you generate some massive states, and then you can think of what's the remaining massless stuff.
Mm-hmm. Mm-hmm. Right, exactly.
May I ask you a related question, please?
Yes.
Suppose you compactify these things to 3 dimensions. Mm-hmm. You expect to get probably n equal to 6, right?
Yes, exactly.
And some of them, maybe you can clarify this point, but some of them, okay, in n equal to 8 in 3 dimensions, this is the quotient was classified by real reflection, right? But the label are somehow similar to you, right? If I do understand correctly.
The label, sorry?
So yeah, so for example, you have something like a G24, G25, and this kind of thing, right?
Ah, yes. Yeah. So you can get, yes.
You can get n equal to 8 in 3D.
So the real, okay, here, sorry, let me draw this nice chart, which, okay, so let's say I have 3D and I can discuss n equals 8 or n equals 6.
Exactly.
And then 4D, I can discuss n equals 4 and n equals 3.
Right.
Okay, this nice chart, by the way, that I'm going to draw is in this paper by Tachikawa and Zafrir.
My question would be related to that, actually.
Oh, okay, great. So yeah, let me just rewrite what they wrote in that table, and then we can explain it. So n equals 3, I just told you, is crystallographic complex reflection group.
Yeah.
So for n equals 4, it's actually crystallographic real reflection group. And
right.
When you go to 3D, you drop the crystallographic requirement. So this one is real reflection, and this one is still complex reflection. So the n equals, so now let's go to this thing here. Let's say, for example, this one that I think you were mentioning. So this guy here is crystallographic if and only if k is 2, 3, 4, and 6. So that means that this guy, this GK1n for k2, 3, 4, 6, could label moduli spaces of n equals 3 theories in 4D or n equals 6 theories in 3D.
Okay.
But if I consider, for example, G5, 1n, that's actually still allowed for n equals 6 in 3D, but it's not allowed for n equals 3 in 4D.
Okay, thank you. Yes, this point, yeah, okay. Now I'm gonna ask, because in that paper that you just mentioned, they missed 2 of n equal to 8 theory, which I think is related to what you call G23 and probably G30, right?
So if you're talking about the n equals 8 case?
Right.
Okay, so n equals 8, right. There's 2, which I think some people call H3, H4.
Yeah, H3 and H4. Can you get it by compactifying your theory on a circle in some way to 3D and then flow to the missing ones?
That's a great question. I unfortunately suspect that, well, we have thought about it, let me just say that, and we haven't been able to figure it out. And I think we tend to think that it's not possible, but yeah, we have thought about it. So it's a great question.
Why you think it's, sorry, I'm really curious about this thing. I mean, I also, okay, it's puzzled me for a long time. So why do you think it cannot be? You have evidence, or it's not?
So, well, let's see what I can say. So first of all, you would have to be, so let's say I wanted to start with the theories I just discussed.
Right.
I would first have to hope that I would get some sort of, SUSY enhancement, right? Because if I just put these on a circle, then I would get an n equals 6 theory. And then I would just have to, pray. So even if this were possible, I think it would be hard to actually check. The other thing is that it was sort of important that the groups that we're considering are subgroups of Weyl groups. Now, both of these groups can be realized as subgroups of Weyl groups.
Mm-hmm.
So you sort of would know exactly where they should come from. And so, for example, I think this one is a subgroup of the Weyl group of E8. So you could just focus on the E8 case.
Mm-hmm.
And yeah, we briefly thought about it and we couldn't figure it out. It might be possible. I shouldn't say that it's not, but we haven't been able to figure it out.
Okay, because the supersymmetry, there's no evidence for enhancement of supersymmetry, basically, right?
Yes, that's definitely. I don't think there's any reason that you would have SUSY enhancement. You'd have to hope for it.
Okay, thank you. Thank you very much.
Yeah, thank you.
All right, so then let's thank you one more time, and I'll really stop the recording now.
Okay.